Okay, so we are going through the basic concepts of traffic engineering. Sorry, it didn't come. Why not? Okay, so we are focusing on learning the basic concepts of traffic engineering. We have gone through the definition of traffic stream, which is made up of vehicles, and we have seen the normal causes of variation in traffic stream. We have seen the types of highways on the basis of traffic flow. We have seen the traffic flow parameters, again 2 types. We have gone through each one of them. Okay, so there are 3 parameters in each of the types. Macroscopic has volume and mean speeds and density, and volume is divided into hourly volume, sub-hourly volume, flow rate, and so on and so forth. And speed was divided into 2 types of means: space mean speed and time mean speed. Okay, which one we normally use for traffic flow analysis? Space mean speed. Okay, then we have the density, and density I told you we cannot get it directly, either we use some equipment or some calculations. Then we have microscopic parameters. We discuss spacing, we discuss headway, and that's it. What was the third one? What is the third microscopic parameter? Anyone? What was the third microscopic parameter? One was spacing, the other one was headway. What is the third one? Average speed. He is saying average speed. He is half right. Mean speed. Very good. Half and half. Full wrong. Speed of each individual vehicle. Okay. Because when we say micro, it cannot be average or mean, because average or mean would mean that it is for a group of vehicles. Okay. So in microscopic parameters, group is not considered. And this is why we did not discuss it specifically here, because speed of one vehicle we know. We did these examples, and then we moved on to this equation, which is the basic traffic flow equation. Okay. Can someone tell me what is V and what is S and what is D? Sorry? Mean speed and density. Okay. And the third one is? Rate of flow. Okay. And we discussed that to apply this equation, the section must be uniform. If the section properties change, then flow will not remain constant. Okay. So if you have 2 lanes here and 3 lanes here, the flow will not remain constant, it will change. Okay. So this equation will break. Okay. S into D will give you one value of V, and here it should give you another value of V. Okay. So you have to keep in mind that this equation gives the same answer until the section is uniform. When the uniformity is broken by any means, by any way, it could be because of a median, it could be because of shoulder, it could be because of intersection, anything. Okay, couple of very simple questions. So our main equation is flow rate equals speed into density. Okay, now look at these questions and tell me, can you solve them or not? So this is my main equation. Sorry. Any problem with any of these equations, any of these questions? Yes. Any problem? What? No means what? No problem, or you cannot do this? No problem. Yes, anyone? Any problem? Yes. Mr. Photographer. Any problem? He is thinking I have bigger problems in my life. Why is he asking about this? Yes. Yeah, bigger problems. My color is getting fade and so, right? I will become the best model of wearing. Okay, 3 parameters, 2 of them are given, you have to find out the third one. Okay, as simple as that. Okay, and both of them we are doing SMS. Nobody does SMS now, right? We do WhatsApp. SMS means what? What is SMS? He's taking his phone out. I got SMS, yeah? No, SMS. What does SMS mean? Space means speed, yes. Okay. A very important thing you need to study is how one parameter affects the other. Out of these three, how one parameter will affect the other. So in these three graphs, you see the theoretical relationships, the hypothetical relationships, which help us understand traffic flow, the basics of traffic flow. These graphs will not be applied as it is, and you will see them. One I will show you now, but you will see some other examples and some other topics. Okay, and if we go on to advanced traffic, which I don't think so, but you may see some different graphs there. But these simple graphs help you understand, okay, how one parameter generally affects the other, okay, in general. But these are theoretical. So at some point, the theory and real world become different, okay, at some point, or at some locations in these graphs, the real traffic flow may not be exactly what the graph is showing. Got it? Okay, and I will show you an example later on. But let us start with the easier one. The difficult one will come in the exam, inshallah. So we have speed and density. We already discussed it in the last lecture. Okay, so density is how many vehicles you have in 1 mile, right? Okay, if I have more vehicles within one space, within a fixed space, what will happen to density? What will happen to speed?
Decrease.
It will decrease, right? So density increases, speed decreases. Clear? Okay. Now the points in these graphs are overlapping. Okay. So if you see a point, this point in this graph, you can locate it in this graph as well if this graph has a speed. Okay, so the graphs are overlapping. You can find the same value of speed in this graph and this graph. Okay, so you need to understand what does it mean. Now going back to this one now. Okay, again a very simple relationship because of the density. If density increases, okay, that means I have more vehicles on the road, right? I have more vehicles on the road. Okay, so what will happen to flow? The flow will increase, right? The flow should increase, right? If there are more vehicles, the vehicles will not stop. They are not there to stop, right? So they come and they move, right? When they're moving, this is flow. When they're moving, this is flow. So if more vehicles are moving, that means the flow is higher, okay? And more vehicles are there on the road, that's why they are moving, right? Okay, so that means density is also high, okay? Now the problem is, you have seen the parking at Juma prayer, right? When you go for Juma prayer, any mosque, any big mosque, let's say Fateh Mosque or something. Okay, you have seen the parking, right? People park anyway. Okay? Because they are going for the 5 minutes of exercise. They know they will come back very soon. Okay? So if you imagine that parking area, how jam-packed it is. Okay, so let's say in that area now there are 200 vehicles. And now you can imagine how they are there. Okay? If somebody comes and he wants to drive within this mess, okay, can he drive smoothly? Okay. So if you look at the density in this condition, the density is what? Very, very high. But what about the flow? Almost none, right? Almost none. Okay. So there is a point of density. At that point, the vehicles are so many, now they are affecting each other. They are not letting each other move. Okay, this is what you see in the parking areas, the busy parking areas. Okay, so if I give you this much space, maybe you can park 3-4 vehicles here, but these 3-4 vehicles will not be able to move. What my point? Okay, so you can have an increase in density with a decrease in flow. What my point? Okay, so there is a portion or a stage in which the vehicles are on the road and they are moving smoothly, no problem. Okay, this is this portion. So you see increase in density and increase in flow as well. Okay, and then you reach a point after which the density is increasing. So there are more vehicles are adding to the space, more vehicles being added to the space. But now they are not letting each other move. There are so many, they are blocking each other now. So density is increasing, but the flow is decreasing. Got it? Clear? Okay. So what is this point where the phenomena changes? What are we calling it? No, the point where the phenomena is changing. It was going up, right? Then it starts to go down. Okay? So it's dense. Critical density. Okay. What about the flow? We call the flow as what? Capacity. Okay. So the point at which the graph, instead of going up, starts to go down. The flow, instead of increasing, it starts to decrease. This is the point where the density reaches critical. And why it is critical? Because now the flow is decreasing. This is the critical point. Okay. If you don't pay attention, you are going towards traffic jam. Okay. That's why it's critical. And the flow at which this happens, we call it the capacity. Okay. When you say this is the capacity of this thing, this is the capacity of this box, or this is the capacity of this flash drive or this laptop. Capacity means what? This is what? When you say this thing is the capacity of this, it means what? This is maximum. Okay. So what were we calling as capacity? Density or flow? What is capacity? Density or flow? Flow. Okay. So capacity of the highway is maximum flow. Okay, or rate of flow to be more precise. Okay, capacity of the highway is maximum rate of flow. Got it? Okay. So you can reach this maximum point, and after this, the increase in density will not increase flow, it will decrease it. Got it? Clear? Any questions? Okay, now you see this similar phenomena in the speed flow rate curve as well, but you have to read it in reverse because we are starting from zero, right? We are starting from zero. So when the flow is zero, why it is zero? Because forget about capacity. Okay, forget about capacity till the exam comes. Forget. Flow is zero because no vehicles on the road. Okay. So if there are virtually no vehicles on the road, then the speed of the road will be very high, right? Because nothing. Okay, you come on the road and you can drive at the design speed, or the speed limit, right? So the speed is very high, but the flow is very low. And the flow increases, that means more vehicles are on the road now, so your speed will decrease. Okay. The flow can increase up to how much? Capacity, right? You call this point as capacity, right? And I told you the graphs are overlapping. So if the maximum flow here is capacity, the maximum flow here is also capacity. Got it? Okay. So the flow can increase up to capacity, and speed will keep on decreasing, obviously. The speed will keep on decreasing. Okay. So when you are going from no vehicles to capacity, speed decreases. When you go from capacity to zero flow. Okay. So what was happening in this region now? Here the vehicles are increasing, flow is increasing. What is happening here? Flow is decreasing because, I told you, right? Flow is decreasing because of what? I told you here. Density, right? Density is increasing. Okay, so the flow is decreasing, obviously the speed will keep on decreasing. Okay, clear or not?
Yes. Doctor, can you repeat?
Which one?
About the flow and the speed.
So when there are no vehicles on the road, the speed will be very high, right? When the flow increases, that means more vehicles on the road. So your speed will decrease. So your speed is going down, flow is going up. The flow can go up to capacity. Okay. Can I add more vehicles on the road after capacity? Yes. Okay. That will be increase in density. But these extra vehicles will block each other, right? I told you here. So when they start blocking each other after capacity, the flow will decrease. Okay. So this is this region now. Clear? Okay. So this region, the solid one, is called stable flow because vehicles are moving smoothly. They are on the road, but they are not blocking each other. Blocking in the sense that they are not stopping each other. Okay. Obviously, the speed will not remain the same. From here to here, you can see that. Is the speed constant? No. The speed is decreasing, right? From this point to this point, the speed is decreasing, right? Okay. So yeah, you are affecting each other but not blocking. Blocking means now I have to stop because of you. Not slow down. Stop. Okay. So this is what happens after capacity. This is what happens in this region. Okay. So when you see the dotted regions, that means the vehicles are blocking each other. They are making each other stop. Okay. Before that, they are moving. Okay. They are moving in a stable manner, continuously moving. Okay, without any stoppages. Okay. So we call it stable flow, and the other one is called forced flow because people are forcing you to stop. Clear? Okay. So one of you already mentioned that when we reach flow, we reach a point on the density which we call as critical density. Okay, and when we reach capacity, we reach a point on the speed which is called as critical speed. Got it? Okay. So what is critical speed and critical density? The values. When do we achieve these values? When do I achieve critical density and critical speed? At what point? This is the only thing you need to remember about critical speed and critical density. Okay? Okay, this is not maximum, this is not minimum. It is the value when the flow reaches maximum. The flow reaches capacity. Okay? Clear? Okay. Now we have studied three things. Rate of flow, speed and density. Rate of flow, speed and density. Which of them is called capacity? Rate of flow. Okay. So this is the maximum rate of flow, right? So there will be a maximum density as well. There will be a maximum density as well. There is a maximum rate of flow. There is a maximum density as well, right? We don't call that as capacity. Because I gave you the example of the parking lot. That is maximum density. Is there a flow there? No. Okay? Clear? Maximum density will not have maximum flow. Okay? What do we call it? We call it jam density. Okay? Clear? Okay, and there is the maximum speed as well. There is the maximum speed as well. Okay? When will I achieve this speed? When the density is almost zero. In order to achieve maximum speed, I need less vehicles on the road, right? Lesser the vehicles, my speed will be higher. Okay? Or some of you are crazy enough to go in jam-packed road at full speed as well. That is your problem. But normal people, okay, the maximum speed will be when you have less vehicles. Okay? Are you guys looking at each other? you guys looking at each other?
There is some.
There's some. Let me know about it. Then give me the registration number of the car. We need to avoid these, right? You never know. Okay. Clear? Clear? Okay. What is the minimum value of these three things in these graphs? Minimum value. The speed, flow rate, density. The minimum for all of them is 0. Okay. When do I achieve 0 speed? Maximum density, jam density. So my speed will be 0. When do I achieve maximum, 0 density? When there is no flow. Okay. And yes, when there is maximum speed. Clear? Okay. When do I achieve 0 flow? 0 density. Correct? No? Yes, correct. When you have 0 density, you have 0 flow, right? 0 density is 0 flow. There are no cars on the road, so no flow. But it is only half the answer. You look at the graph. Yes. Yes. Jam density is also 0 flow. Okay. So 0 speed can only happen in one condition, jam density. 0 density can only happen in one condition, which is 0 flow. But 0 flow can happen in two conditions. One is this side of the graph, the other one is this side of the graph. See, both of them are 0, right? This is 0 because no cars. This is 0 because cars are blocking each other. Okay? So 0 density will have 0 flow and jam density will also have 0 flow, but the reasons are different. Got it? Clear? Okay. And similarly, flow, you can have the same flow on this side and on this side. See? Point A and B. Is the flow changing? No. Okay. But is the condition changing? Yes. Okay. So, you will see later on that they are non-linear. That's why they are the curves. They are the curves. Okay. So, I was telling you the graphs. These graphs are simplistic and they are hypothetical, theoretical, just to understand the phenomena. Okay. This is what you guys have done to traffic. Quite literally. It's written in the book. Like not by your names. Okay. Ali did it or Hassan did it. But they are saying young drivers did it. Okay. So this is the graph between flow rate and speed. The graph between flow rate and speed. Now keep the real thing in mind. Okay. And I will draw it here as well, just to change the orientation. Okay, so the flow rate and speed is this one. We are talking about this graph, right? Okay, but they have changed the orientation. Here it is vertical. If I make it horizontal, it will be like this, right? Okay, this is my capacity. Okay, clear? Okay, this is the actual graph. Okay, now if you look at this graph, there is no region 1 here. Region 1 is showing what? A straight line. Okay, so just trust me, there is no straight line. When I make something, I don't know where my hand goes. Okay, so the AutoCAD is invented because of me. The computer is invented because of my handwriting. So this is the thing. Okay, I am the initiator of many innovations. Okay, but there is no straight line here, so there is no region 1. A straight line is representing what? Constant. Region 1. What is constant? Constant speed. Okay. Theoretically, if you add one more vehicle on the road, the speed should reduce, right? Theoretically. Okay, but does it? No. Okay, because we are very brave people, right? Somebody told me the red color in the flag of Bahrain is for bravery, right? Right or wrong? You don't know, you don't know. Shame on you. Okay. So the point is, the flow and the speed do not normally interact with each other one by one at every point. Okay. So there is a point up to which the speed, the drivers do not try to change their speed. Okay, just like this chair. For 15 minutes, nothing happened, right? The same person was sitting here. So the speed is constant, region 1. Theoretically, there is no region 1. This is called the aggressive nature of the driver. Okay, this is what they have found, that this change is necessary because of the new trends of the drivers we have and the vehicles we have. Okay, now the braking system is more efficient, the acceleration is more efficient. Okay, the drivers are using their phones more. They don't even know that there's another car in front of them. Okay, so there's a region 1 which is called the aggressive region. Okay, or the region which is showing the aggressive nature of the drivers. Okay, they will go at the same speed even if the spacing is getting less. Okay, this is the whole point. Region 2, this one. It's a graph, it's a graph. It's a curve going down, it's a curve going down. No change here. Okay, so this is where it starts to happen. Okay, that you see the flow increasing and you react immediately. Okay, now the spacing is less between me and the other car, I should reduce my speed immediately. Okay, you will not go very close now. Got it? You have reached the threshold up to which you can get to the other car, close to the other car, and still keep your speed. This is your threshold, the end of region 1. Okay, and they are calling it what? The break point. Okay, we will use these points in another lecture, and that will come after many days, so you will forget it, I know. Okay, but just fulfilling my duties. So this is the break point. Okay, your threshold up to which you will not, or after which you will not maintain your speed. Got it? Okay, then we reach this point. This point is maximum of flow. The maximum flow is called capacity. Okay, now after this, if you look at the theoretical graph, we start to go back, right? We are going back how? In a smooth curve, right? But this is how it actually happens. It's not a curve, it's a drop. Okay, it does not go back smoothly, especially for some portion. Okay, now in this portion, you notice the change in flow, small, and you notice the change in speed, big. Got it? Okay, this is what they call as Q discharge point. Okay, or the point after which the Q discharge will happen. Okay, this is basically region 3 is the formation of the Q. Okay, region 3 is when the traffic jam has just started. Okay, so you are coming at very high speed. The speed is very high, right? And then you will see the car in front of you is now very slow. You will do what? You have to suddenly press your brakes hard. And after that, you will move very, very slowly as per the other car. Okay? Maybe you will stop and move, and so on. So this is what will happen after that. But initially, people are coming at very high speed. Okay? Because they don't see the queue. After this point, now the queue is very long. These many people are already in the queue. So even before I reach to the end of the queue, I know that there are so many vehicles which are stopped now. Okay, so I come and join at low speed. So my transition is very smooth now. Got it? Clear? Okay, so this is a broken curve. This was a very smooth curve, you can see. This is a broken curve. Okay, only 2 regions out of the 4 are following actually a curve. Out of the 4, there are 4 regions, right? 1, 2, 3, and 4. Out of these 4, 2 are following the curve. Okay, the others are, this one is a straight line and this one is a dip. Okay, almost a straight line. Clear? Okay. To solve this issue, to make it much smoother, I don't have the curves for that, but in some countries they use variable speed limits, okay, or driver warnings. Okay, so before you reach to that point, you will get a warning that there is a traffic jam ahead.
They have LED screen showing there is traffic jam.
Yes, yeah, they use LEDs. Even for variable speed limits, they use LED screens. Okay, so there are screens on the road at specific points, and you see the screen. You don't see the queue in front of you, but you know that you will reach that point. Okay, so you may change your route. This is one option. Okay, why should I go there? I have another way. I can go with another highway. Or the other thing is, okay, I just joined the traffic jam, so I can relax. Take my phone out on something, right? Sleeping or awake? Okay. Keep on pinching him. Okay. Or the other option is, instead of the warning signs, they use variable speed limits. So you are not coming at this speed. When there is a traffic jam on the next segment, they will reduce the speed limit of the previous segment. Okay, so drivers do not come at fast speed and join the queue. Okay, this solves two purposes. When you reduce the speed limit of the previous segment, it will solve two purposes. You know, sometimes or many times it happens, you are coming at very high speed, you don't expect the other car is slow or stopped, and you go and hit it, right? So it solves the problem of the accidents which can happen in this way. And the other thing it solves is the increase in queue. The people are coming at very high speed, but they are not going at the same speed. So what is happening? The queue is increasing. But if you slow these people down, the queue will increase, but with less speed. What my point? Okay. So, anyways. So this takes us to the concept of traffic flow theory. Traffic flow theory is a combination of equations which explain the phenomena of traffic flow. Okay, traffic flow theory is the combination of equations which explain the phenomena of traffic flow. Okay, and those equations follow the charts and graphs which I showed you. Okay, and it started in my childhood, 1930s. Okay, the first set of equations they came up with was between speed and density. Okay, so we know this, right? Density increases, speed decreases. For the sake of developing the equation, they said that this is a linear phenomenon. Okay, this is happening linearly. So there's a linear relationship between speed and density. Okay, so it's a straight line. What is the equation of a straight line? Yes, tell me. The equation of a straight line.
Y equals
C
X
X plus D whatever D B. Okay, something like this, right? Okay, and look at the graph. Tell me what is my Y.
S
S. What is my X? Okay. What is my D? D. This one.
65.
Huh?
Minus 65.
65, which is what?
When
On the y-axis, right? D is supposed to be on the y-axis, right? Where the graph intersects. The intercept, right? D is the intercept. Right or wrong? Yes. Clear? Sure. Okay. So 65. And what is my C?
Minus 65 minus 65 over 110.
See again?
Minus 65 over
What is this?
It's like a ratio.
Slope.
It's a ratio.
Slope.
It's a slope. Okay. C is supposed to be the slope. Okay. So slope means y upon x, right? So what is my y? 65. What is my x? 110. Okay. So 65 upon 110. Okay. Clear? Clear? And the line is going down. So down means minus. Okay. Any problem? This is the same equation, right? Is it?
No, not the
No?
minus.
Other, right? What's your name?
Zero.
Huh?
Zero.
Yeah. Okay. This is the same equation now.
No.
No? Why did you say this? Yes. It is the same equation. Maybe. Say no. Maybe. Same equation. We should do voting, right? Democracy. Yes. Why are you saying same equation?
Because of the 64.
Yeah.
Except
There is 65 there. I took it as common, and this is what we get. So same equation. Okay. These are same equations. Okay, just simplified it. Clear or not? Any problems? Any questions? Okay. Now we have this equation, and I already showed you the equation which I called as a basic of traffic flow. Okay, that was V equals S into D, right? Okay, so if V equals S into D, then S equals what? Okay, so I can put S as V over D, right? Okay, so V over D equals to 65 1 minus E upon 100. Okay, clear? Okay, now tell me V equals to what?
65D,
65D.
1 minus D over 1.
65D and still 1 minus and so on. You open the bracket, right?
D squared.
D square, yes. So 65 D square. Okay. My mark. Okay. Any question? Open the bracket, multiply the D's. Okay. Okay. I'll go back to this equation again. Okay. So, no, sorry. Before that, so this is 65, this is 110. Okay, so you can calculate the ratio, right? So instead of writing 65 on 110, I can write the value, whatever it is, point something something. Got it up till now? Any problem? Obviously, no problem. I'm doing it, right? Okay, going back to the first equation. Okay, so V equals S into D, right? So D equals to what? First equation. V over S. Okay. So now I will go and replace the value of D here. Okay. This was my actual equation. I will replace the value of D here. Okay. So S equals 65. Opening the bracket now. 65 upon 110 and D equals to V by S. Okay, clear? Okay, then according to this, V equals to what? Tell me. What is V equal to? You have to reverse, right? You have to reverse the whole equation. So V equals to what? Abrar Raid, Adil Muhammad, Ala Adil, Hashim Ahmad, Habra Ahmad, Hussain Jafar, Muhammad Khalid, Umayma Yasir, Salil Fahim. Yes, Salil Fahim. Sayyid Muhammad Haider, Sultan Turki, Zainab Abdul Hussain, Zainab Ali, Ziyad Jasim, yes, V equals to what? Huh? Something wrong. Say again. One thing missing. Like you are in one group, right? For senior. You need to combine. Then you will get the right answer. Yes? Anybody else wants to show me your tablet? No, it's still something missing. I think. Not okay. You were missing S and you were missing what? That's what there. I know. Sorry. Okay, so V equals to what? What is it? 110 S minus 110 upon 65 S square, right? Minus is with the ratio, right? The minus is with the ratio.
X is outside.
Yes. Any problem?
Are we going to use those equations?
Sorry?
Are we going to use those equations?
No, you're just being fine.
No, doctor, but you said the relationship isn't linear.
The relationship is not linear, see? S square means okay. There. Any problem? with anyone. See, I'm not asking these people who actually did it. Even if there's a problem, they can deal with it. I'm asking those like kings and queens who are here to see how their slaves are working here. Fine or not? Okay, no problem. Okay, so these are the equations, the same thing done, and the ratios, there was a ratio, right? In each equation there was a ratio. 65, 110, 110 to 65. So these are the values for the ratio. Okay, so there is no difference between this one and the previous one, only the ratio. Okay, the ratio has been calculated. You can see the process over here as well. So you don't have to work basically. Okay, now we will use these equations to calculate the capacity of the highway. Okay, we'll use these equations to calculate the capacity of the highway. Okay, what was capacity? Remind me, what was capacity? Maximum rate of flow. So I'm looking for maximum value of which parameter? V. I'm looking for maximum value of V. How many equations for V I have? Two, 3. Okay. So I can use any 3 of these equations, right? If I use this one, I need S and D both. Okay. If I use this one, I only need D. If I use this one, I only need S. Okay. Now going back to the graph. Okay. This is my maximum, right? Okay. And this is the equation of the curve which I have. V and S. Okay. So I'm talking about this one. Okay. It's a graph and so on and so forth. This is the point I'm looking at. Okay. What is the slope at this point? 0. Okay. When slope becomes 0, what would I put as 0 here? The first derivative equals 0. Okay. The first derivative means the slope. Okay. When you have a quadratic equation, the first derivative of that equation gives you the slope. And we are saying that that is equal to 0. Clear? Okay. So my first derivative for this equation, I'm talking about V, the equation between V and S, the last one. Okay. So I'm doing dV by ds. Okay. So what is this? If you take the first derivative, what will you get? 110.
The second equation.
The last equation, yes, 2 times 2 times what? 1.6923 and S equals to 0. Okay. What is the value of S? Hmm? 32.5. Okay, any problem up till here? Okay. I can repeat the same process here. Second degree equation. I'm still looking for the maximum point. Maximum point will have a slope of 0. For the slope, I will take the first derivative and put equal to 0. Okay, and this will give me the value of what? D, right? Okay. Now, before I calculate that value, and this is very important for you keep these things in mind. Sometimes I will see students who will do from the first step till the last step, just because we did it in the class. Okay. So you need to keep your brain present for what is required from you. Okay. In the last course, in the final exam, there was an equation missing. There was an equation missing in the question paper. Nobody asked about it. I missed it and nobody asked. They were busy doing all the steps from the start till the end. Okay, and because there were some parameters which are in the question, and the equations were given for the other questions, they did everything. Okay, nobody asked me for that equation. Okay, because the question was slightly changed from the class. Okay, so you need to think what is given, what is required. Okay, why did I do this? What was my question? We are trying to calculate critical speed, capacity, right? I calculated this to calculate capacity. Now answer me this. Can I calculate capacity without doing anything else? Yes or no? Yes. Okay. I'll take this value, I'll put it over here. I needed S, right? I have S. Okay, so I can calculate capacity. Clear or not? Okay. What do we call this? S? You said it. Critical speed. Okay, this S value you calculated, which happens at capacity, is called as critical speed. Okay. Now, just for fun, we will do the same thing here. Okay, this will give me critical what? Density. So what is critical density? Tell me.
55.
55, but just by looking at it.
No, I think so.
What type of statistician are you? You just tell me that by looking at it. Yes.
54.9.
54. See?
She have a mistake.
0.99.
Calculator error.
Yeah, right.
Calculator. Okay. Can I calculate the capacity? But now I can calculate it from this equation and from the first equation as well, right?
Yes.
So now you have the S and D both. Okay. Use any of the equations. Tell me what is capacity. How much is my capacity? Capacity is V, right? Which V? The maximum. Okay. So don't ask me that where is the equation of capacity. Maximum V is capacity. Yes.
But if you have the equation, give me a different answer.
How much different?
1819.
Really? Which one? Third?
Third one.
Okay.
52 vehicle different.
Yes, any problem. You can get some difference because we are taking ratios, so it depends upon how many decimal places you are going up to. So instead of 55, I put 44.9, I can get slightly different answers. I can. Clear? Okay. So normally for speed and density, we go up to 1 decimal place. For flow rate, no, nothing. Okay. But again, we get 87.5, somebody may do 87, somebody may make it 88. There can be some difference. Okay, no problem. Did you understand what we have done? We looked at the linear relationship between speed and density. We came up with the first equation, that one. Then we used the basic equation of traffic flow and came up with the other two equations which were for flow rates. So now for flow rate, I have 3 equations. Okay. And to calculate maximum flow rate, I took the slope and put it equal to 0, the maximum point of the curve. And using that identity, using that property that the slope should be 0 at maximum, I calculate the critical speed and the critical density. Okay. Then all 3 equations are open for you. You can use any of them to calculate the capacity. Okay. This is you can see we are looking for the same things, okay, but the equation is changed. The equation between speed and density has changed. Okay, this was the equation in this example. Okay, this one. You see 65 here, 110 here, and then you see here 71.2 and 120. Okay, so numbers have changed. Okay, what about the type of equation? Same. Okay, the numbers have changed, the type of equation is the same. Now what are these numbers depending upon? 71.2 and 122. So this was, here it was 65 and 110, right? What was 65? Maximum speed, right? Okay, we call it free flow speed. Free flow speed. And what was 110? Maximum density. We call it jam density. Okay. Now maximum speed of the road depends upon what? Maximum speed of the road, not of the drivers. The road itself depends upon the design. Okay. So when you will change the design, these numbers will change. When these numbers will change, your equations will change. Okay. But the trend will remain the same. Okay. We have the same type of equation. Okay. Now, part B and C, you will do it yourself. The same thing which we have done just now. Okay, the same thing which we have done up till now. But part A, they are asking for free flow speed and jam density. I already showed you in the graph, right? What is free flow speed? What is jam density? The trend is the same. Okay. So how do I calculate? So for free flow speed and jam density, I don't need any other equation. I can tell you from here. What is my free flow speed and what is my jam density? How do I get it? Yes? 71.2. Okay, and how do I prove that this is my free flow speed?
Solved by 0.
Huh?
Solved by 0.
So what should I put as 0?
D 0.
D as 0. Free flow speed, right? Maximum speed. So when the speed becomes maximum and the density is 0. Got it? Okay? Clear or not? And what is this 122? Jam density. And how do I prove this is my jam density?
Speed by 0.
The speed is 0. Okay? This is easier to remember, right? There's jam speed is 0. Okay? Clear? Okay. The part B and C means you will do all this derivation. Starting from here and what? Yeah, starting from here and then this one. Clear? Okay. Any questions? Okay. One thing, in this equation, applying the same logic which you said about the new question. What is my free flow speed here? 65, right? Okay. And when you calculated critical speed, it was 32.5, right? Do you see a relationship between this one and this one? Huh? It's half, right? Okay. So critical is half of free flow speed. Okay. Critical is half of free flow speed. And what about this density? Can I do something like this for density as well? Critical density? Yes.
It's half of
Half of?
critical density.
Half of critical density? No.
No, the critical
Critical is half of
jump density.
jam density. Okay. So my jam density was 110 and you got critical 55 or 54.9. Okay. Like I said, it's almost like it's approximate. Okay. So now remind me what was critical speed and critical density. What is the definition of critical speed and critical density? When the fluid is the capacity. Okay, before we move on, very important points. A lot of students make mistakes in this. Okay, you have to keep the variables separately. Okay, you have to treat them separately. Okay, so if I ask you for capacity, I'm asking you for maximum flow rate. You cannot give me a density or a speed and say this is my capacity. Okay, okay, and the maximum of density and maximum of speed. Are they at the same point? The maximum of density and the maximum of speed, are they at the same point? No, they cannot, right? How can you have maximum density and the speed is still maximum? Remember the parking lot example. Okay? And the critical, are they maximum values? Okay? So just because I am saying capacity, everything doesn't become maximum. Okay? The speed is maximum, the density, no. Okay? Clear? Now we move towards interrupted flow facility. So there were two types of traffic flow facilities, interrupted, uninterrupted. What we have been discussing is for uninterrupted flow facilities. So first of all, tell me the difference between them. What is the difference between interrupted and uninterrupted?
What do you have? No, it is full control access to the highway. No access.
Meaning, no,
No,
no intersections. Okay. So when there is an intersection, you may have to stop because the signal is right. Okay. Or maybe there is no signal, but you may stop because some pedestrian is crossing, the car is coming from the other side. Okay. The equations which you have seen up till now, is there any element of signal here? Is there any element if the car is crossing or the pedestrian is crossing? Okay, so these equations cannot work at intersections. Okay, because they are missing the critical part, the important part of the intersection, which is stopping because of some other reason. Got it? Okay, so these equations cannot be applied on intersections. Okay, so these equations are mainly for uninterrupted flow facilities. For uninterrupted flow facilities, because they are under the influence of other movements. Okay. What happens after the intersection? So you have crossed the intersection. Usually vehicles enter the intersection in the form of a group. And this is very obvious at the signals. Okay, the signals is very obvious. But even on roundabouts, you will see, you will get a chance to enter when there is no traffic from the other side, right? And when you enter, what will happen to the other lanes? They will enter with you, right? Because they are facing the same movement. So when you get the chance, they also get the chance. And if the chance is longer, no vehicle from the other side for a longer time, what will happen? The vehicles behind you will also enter. Okay. So the point is, you cross the intersection in the form of groups. Okay, because you are crossing when you don't have any interruption. Like that, whatever the reason of the interruption was, now it is not there. The signal, the other movement is not there. So when you get the chance, you will have a group of vehicles which will cross together. Okay, those group of vehicles are called as platoons. Okay, so they are moving together on the road. Okay, I have just crossed one intersection. Now I see a road in front of me and I have cars around me. Okay, cars or vehicles or whatever. Okay, and there is no other intersection up to 5 kilometers. So what will happen in these 5 kilometers? Will I stop because of any external reason? No. Okay, in this part, will these equations work? Okay. So these equations will obviously work on uninterrupted flow facilities because they don't have intersections, and these equations will work there. Okay, but even on interrupted flow facilities, when you cross the intersection and you are not near the next intersection, you can still use these equations. Okay, so in that sense, these equations are not applied on the whole highway. They are applied on a part of highway, on a group of vehicles. And what do we call the group of vehicles? Platoons. Clear? Okay. The main point is, these equations will only apply when you don't have any external interruption. The equations will only apply when you don't have any external interruption. If it is for the whole highway, uninterrupted flow facility. If it is a part of the highway, maybe it's an interrupted flow facility. But in this part, there is no interruption. Okay, so these equations will still work. Got it? Clear? Okay. We have already discussed about volume and capacity, right? What was capacity? Maximum rate of flow. What was volume? Vehicles per hour. Always per hour or more. Okay. So you understand these things, right? Which one of them is a constant? Which one of them is a constant? Volume or capacity? Capacity. Okay, capacity is the constant. The design of the highway it will not change. Huh? You calculate a number here, right? In the previous example, we calculated number 1,700 something something, right? This number will not change. Okay, but the volume, will it remain same throughout the day? I have 2,000 vehicles in this hour. Next hour again 2,000 vehicles? No, right? This changes according to what? According to demand. Okay, the volume changes according to demand. Capacity is something which we fix when we are designing the highway, but volume, actual volume, increases, decreases according to the demand. Demand is how many people want to use the highway. Okay, how many want to use the highway? Normally, all three of them are measured per hour for traffic flow analysis. Okay, for traffic flow analysis, normally all three of them are measured per hour. Okay, is there a possibility that the demand can go above the capacity? Yes. Okay, that's where we have the traffic jam, right? That's when we cross the capacity. I showed you the graphs as well. So what are the possible actions that drivers can do? I already gave you one example. Okay, if you see a warning sign, traffic jam ahead, okay, you can do what? Then go to another route. Okay. If you get the warning even before you start the trip, then you can do what? Not go. Home is clean and nice and AC is working, and just sleep there, right? Not go, right? Or what else? Drive on the shoulder. Huh? What did you say? Drive on the shoulder. Okay. Yes, that one. Or get like a bigger car, Silverado or something, and you drive over the other car. What's the problem? Okay, yes. Any other bright ideas? I told you if you get the warning even before the trip, so you haven't started the trip, you are not in your car. Go somewhere else, obviously. Who needs to go to the class every day? And change the trip. Like how? Anywhere else or? Delay the time, change the time. Okay. So all these options are there. Okay, changing the location. It depends upon the type of trip you have. If it's a work trip, then the location is fixed, the time is fixed, you cannot do anything. Okay, you just get in the line. That's it. But for the other things, going for shopping or something, you have the option to do other things as well. Staying home is an option as well. You should take this more often. Okay, but the point is, if any drivers are taking these options, and I go to the site and I start counting the vehicles which are on the road, will I get the real demand? No. Okay, it does happen. It does happen. We do this every day. We know this road will be congested, this will happen here, this will happen here. Okay, so we make our decisions, but now we are used to it. Okay, then I have to go for this thing on this time. I have to go for this thing from this side. We are used to it now, but we are making these decisions. But if somebody told me that on this highway, now there is no traffic jam, I may go on to that route. Okay, so the actual demand may not be on the road itself. Okay, the actual demand of the highway may not be always on the road itself. So you may have to go to, I mentioned in one of the previous classes, there was a question as well. You have to go to your planning studies to see what is the actual demand of the road. The actual demand may not be how many vehicles you see in front of you on the road. Okay. Okay, we will do it next time. Any questions? Okay, since there was